Hello, ladies and gentlemen. This is Dean from Mostly Pi, and this is Linear Algebra. In episode 2, we mentioned that the solution to a matrix is called the null space. In linear algebra, matrices have some properties that we'll get into later, but they're all defined by some operator and an argument. For example, a null space is null A, where null is the null space operator, so null A refers to the null space of matrix A. However, there are other vector spaces. In general, we reference Rn, which is an arbitrary linear manifold that spans an arbitrary / unimportant number of dimensions. Specifying n to describe a specific space along coordinate axes gives us things like R3, which is a three-dimensional volume, R2, which is the XY plane, and R, or R1, is the number line. And this can go up as high as you want. Alternatively, R0 is a zero space, which only consists of the zero vector. It also has zero dimensions, meaning that it's a bit trivial, but it does mathematically exist. A vector space is simply an object like a volume, plane, line, etc., that has some certain properties. First of all, it cannot be empty, which the existence of R0 makes difficult because almost all spaces contain the zero vector, although some conditions omit the zero vector, so those are not vector spaces. Also, any vector in a vector space will also have every one of its scalar multiples in the same space, which is called being closed under multiplication. This means that half spaces are not vector spaces because the negative multiples lie outside the space. Additionally, any two vectors in a vector space will add up to another vector in the same space, which is called being closed under addition. This means that no sum of vectors can possibly lie outside of the original vector space. And these rules apply fairly obviously to the objects we've looked at, as they extend infinitely, and it makes sense too, because if you think about it, try reaching the fourth dimension yourself. It isn't exactly possible, because we exist in a hypothetical R3 of sorts and consist of third-dimensional position vectors. So you don't possess a fourth spatial component, and you can't move about 4 space. Any vector that fits these three rules is defined to be, any space that is, that fits these three rules is defined to be a vector space. Sometimes spaces exist within a higher space. This means that these spaces are subspaces of the higher space. All a subspace means is that a vector space exists within a larger or equal space, which, yes, a subspace can exist within itself. This is proven in a similar way of proving that a space is a vector space, with the additional caveat that you have to show that every vector in the subspace is also an element of the higher space. And to prove that the vectors are mutual, we need to understand bases, which is the motivation for the next video.